once again, welcome to the first session on this algorithms for competitive exams, STTP. So here we are going to discuss algorithms mainly in point of view of competitive exams and whatever theory which is required to solve problems. That theory also we discuss in detail, and mainly we focus on this syllabus which we have mentioned in our brochure also. I'll get computer science 2022 syllabus. That is what the topics mainly searching, sorting, hashing, asymptotic analysis, divide and conquer, dynamic programming, greedy method, graph traversals, minimum spanning trees, and shortest path. I may not exactly follow this order, but we cover all the topics whichever are there in this syllabus. So initially, in order to understand completely any algorithm course or in algorithms textbook, okay, first we need to understand what does computational problem mean, what is the computational model that is used for analyzing algorithms, what does asymptotic analysis of algorithms, and what is the difference between problem complexity and algorithm complexity. These are like ABCDs of the course. Okay, ABCD of the course. We will try to understand what does computational problem mean. Now, in the algorithms, so it is the course is actually called as analysis and design of algorithms, or design and analysis of algorithms, or algorithm analysis and design, whatever it might, different names, different names. What for we write algorithms? What for we write algorithms? So we'll make it interactive. What for we write algorithms?
Programmings. We can construct program.
Step-by-step procedure to solve any problem.
That is definition of algorithm. So my question is, what for we write algorithms?
Problem solving.
That is to solve problems. Next question is, what type of problems we solve? What type of problems we actually consider here? So do we consider problem of always remaining happy forever?
No, sir.
Sir, can you repeat, please?
Okay. So what type of problems we consider here? Okay, we write algorithms to solve problems. That's what someone has said. So next question is, what type of problems we solve here? So do we solve?
Sir,
are we going to solve problems like this? How to live happily throughout our life?
So, while writing an algorithm, we consider the problems. Those have some specific steps to solve it.
Okay,
it should not be like it work on an infinite loop or don't have any definite solution. We don't consider these problems for writing the solution.
Logical problems can be solved.
Even see how to live happily. Okay, no, some people initially, if a boy or girl of 10 years old, if they ask no, then people or parents, they might say that, okay, well, okay, study well. Then after that you get a good job. Okay, then after that you get good salary. Then you'll be happy forever throughout your life. After that, go for marriage or whatever it might be. Okay, does it work for everyone, or is the procedure is this: work, study well, then get a job, and with that you get a good nice salary, okay, handsome salary. Then go for marriage. After that you will be happy with your parents and your children throughout our life. Are we going to solve this type of problems?
No, sir.
No. Or how to become rich in 2 years? How to become rich in 2 years?
Sir, again, this problem doesn't have any stable solution. or a definite one that can be followed by every person in every situation. So I don't think.
But mainly our intention itself is not to solve this type of problems. For what type of problems we solve? There must be some computation involved in it, and we want some computing device like computer to solve it for us. Once it is told what is the procedure that need to be followed, then it has to give answer for any input which we give. That is our intention. No? That type of problems only we consider. No? Are we going to consider this type of problems whenever we say algorithms for a problem? No, we are not going to consider this type of problems. Then what type of problems are considered? What type of problems are considered? What type of problems are considered? Some computation is involved in it. So computation is involved. And who has to do that computation? Who has to do that computation for us? Are we going to do for each and every instance of the problem? Who has to do that computation for us? Some computing device. Some computing device. Some computing device. And what is the computing device that we are going to consider here? Computing device like, say, computer. Okay, is that okay? So we consider problems where some computation is involved in it, and we need some computing device to solve it for us. Once it is told what is the procedure that need to be followed to get transform input to output or to get answer for given problem. Is that okay? That type of problems only we consider. And these type of problems are called computational problems. Okay, now what are they called? They are called as computational problems. Computational problems. So can you give an example for computational problem? Can you give an example for computational problems?
Factorial of a number.
Finding factorial of a number. Okay, one is factorial of a number. Factorial of a natural number. Let us write it as a natural number. Next, any other example?
Is the longest common sequence or the least common sequence?
Okay, longest common subsequence. Okay, longest common subsequence problem. Any other? I'm asking for problem names only. Okay.
GCD of two numbers.
Adding two numbers. Okay, no. So like this, we can give many examples now. So give me some more problems, general names. We have different problem types now. Can you give different types? Any searching problem in our syllabus also it is there. No, searching problem is one problem. Searching problem. Any other problem? Any other example? Sorting problem.
The sorting problem.
So like this, we have different problems. No, these are all computational problems. No, or in our textbook, whatever is given, any algorithm textbook, all are computational problems. No, not only algorithm textbook. In computer science or in engineering field, whatever we solve, all are computational problems. We want some computing device to solve it for us. Okay, all are computational problems. Okay, please, all of you see this. So what is a computational problem? That is a task which computers might be able to solve. Okay, no, computers might be able to solve. Here we are not worried about what is the amount of time they take. Okay, whether is it possible to solve or not? It is possible to solve or not. Now these are some examples. Given a positive integer, determining whether it is a prime or not. Is it a computational problem or not? Whether it is a prime number or not. That's a computational problem. Similarly, whether given number is even or odd. That's also a computational problem. So next one is that is a sorting problem. Given a graph, finding maximum independent set of that graph. That is also a computational problem. So given a graph, finding Hamiltonian cycle of that graph. That is also a computational problem. So like this, we can give many examples for computational problems. No, computational problems. Okay. That is fine. Now we know that we are going to consider only a computational, some computation is involved in it, and that type of problems we consider. Okay, we consider. Next, how to, we have a computational problem. Next question is how to formally define that problem. Any problem, first we need to formally define. To formally define, we need to say what is input to that problem and what is output. What is output? What is input in case of sorting problem? What is input in case of sorting problem? What is
Sequence
input
of
in case of
numbers.
sorting problem? So it is, we can consider it as a sequence of n numbers, a1, a2, and so on, an, a sequence of n numbers. What is output? What is output? What is output? For example, we are given a sequence 8, 2, 5,
Ordering problem.
4, 3, something like this. We are given a sequence of 5 elements like this. What is output? If this is input, what is output we actually expect?
Either ascending or descending order.
That means we need to rearrange these elements, this sequence of 5 elements, such that what is the condition it has to satisfy? What is the condition it has to satisfy? Total, say we are given 7 elements. We need to rearrange these elements such that some condition. What is the condition that it has to satisfy?
Non-decreasing values.
That is, first element is less than or equal second element. It is less than or equal third element, and it is less than or equal last element. So if we assume that all elements are distinct, if they are distinct. Okay, now in this case, answer is 2, 2, 3, 4, 5, 6, 8. Correct now? Okay. But if we are given, this is 1. If we are given distinct elements, 8, 2, 5, 3, 8, 2, 5, 3, then this we can call it as a permutation of these 4 elements. Our output is a permutation of these 4 elements such that first element is less than or equal second element is less than or equal third element is less than or equal fourth element. No, so that is actually sorting problem. Is that okay? So what is input in case of sorting problem? A sequence of, say, n distinct elements. We can allow even equal elements. A sequence of n distinct elements, if we consider. What is output? A permutation or reordering of these elements such that first element is less than or equal second element, less than or equal third element, and so on. Okay. Is that okay? Now, what are the specific values we give for A1, A2, A3, and so on? So what, this is the first value, this is the second value, this is third value, this is fourth, this is fifth, sixth, and seventh. These are the specific values we are giving for input defined in sorting problem. No, that becomes an instance of the problem. Now, in this case, what is instance? Here, this is it an instance of the problem or not? 20, 18, 68, 42, 90, 82. Is it an instance of the sorting problem or not?
Yes.
Yes. What is the, how many elements are there in that instance? 6 elements. How many elements are there in instance? 6 elements. So yeah, if I change n value, in this case, how many elements are there? 7 elements. This is also an instance. This is also an instance. In this case, there are only 4 elements. This is also an instance. That means instance can have, need not have always same number of elements. No, n can be different. So that's why we can consider it as a parameter. Now, what is size of input? What is size of input in case of sorting problem?
10.
So what does actually size of input mean?
The number of elements which we are interested in sorting, sir.
Actually, input size means amount of memory that we require in order to represent a given input. In order to represent this, what is the amount of memory that is required? That is actually input size. Amount of memory required to represent the given instance, that is actually input size. But loosely speaking, what is input size here? How many elements are there? We'll come back to this after some time. Okay. Loosely speaking, what is input size here? Input size we can consider it as number of elements given to us. Here, how many elements are given to us? 6 elements. So that's why input size is 6. In this case, input size is 7. Here, input size is 4. Okay. Input size is 4. That means input size, we have a parameter. In this case, that parameter is n. We have a parameter is n. If it is a problem related to matrices, for example, matrix addition, what is input size in case of matrix addition problem? What is input size? What is input size in case of matrix addition problem?
Number of rows.
So we should be given 2 matrices, no? Okay. Here each matrix will have some number of rows and some number of columns. Here it is same number of rows, same number of columns. Okay. Matrix addition problem. So here in case of matrix addition, what is input size? Is it 1 parameter as given in sorting problem, or it is more than 1 parameter?
More than 1 parameter.
So input size can be a 1 parameter, or it can be more than 1 parameter also. So in case of matrix addition problem, what is input size? Number of rows as well as number of columns. That means how many parameters we have for input here? 2 parameters. We have 2 parameters here. So if it is anything related to graph problem, something like this, it is simple and directed graph, something like this. What is input size?
The number of edges and number of nodes in that cell.
Not only number of vertices as well as number of edges, that we consider as input size. In case of graph problems related to graph, number of vertices as well as number of edges we consider as input size. Now this problem, so please tell me what is input size. What is input size in case of searching problem? Whether it is 1 parameter or it is more than 1 parameter. 1 parameter is substance, no? 1 parameter n.
Yes,
number
1
of elements
parameter
given
n.
to us. Okay, number of elements given to us. How many parameters we have here?
2 parameters.
N and m, 2 parameters. Number of rows as well as number of columns. How many parameters in case of matrix multiplication?
3 parameters.
3 parameters here. Sorry, 2 parameters, n and m here also.
No, if there are 2 matrices, one is n cross m, another one is m cross p.
No. See, matrix multiplication, number of rows should be given and number of columns should be given. No, number of rows and number of columns. That's all.
In matrix multiplication, if there are 2 different size of matrices, the unique instances will be 3.
That is okay. That is fine. But here, what we are talking about is, here this is what you are saying is this is P by Q. This can be Q by R. Still multiplication is possible. That's why here you are saying this is 3 parameters.
Yes.
Is that okay?
Yeah.
Okay. So in that case, for example, if I take square matrix, now whether we require only 1 parameter or 2 parameters?
No, if problem is well defined with square matrices only, then 1 parameter.
So that is why 1 parameter we are saying is actually that is not 1 parameter. Actually, we have number of rows as well as number of columns. That means n square entries are there in our matrix. No, n square entries are there. N square elements are there. N square elements. If I want to represent this n square elements in memory, how much memory is required? It is actually in terms of n square into maximum amount of memory that is required to element the largest element which is present here. No, the largest element which is present here. No, for example, say we are representing in binary form. So how many bits are required? Here some number of bits required. The total amount of memory is not more than n square into number of bits required to represent the largest element present here, no? Is that okay? Is that okay?
Yeah, if we'll consider the space analysis also, then it is fine. But if we'll talk about only parameter, and if it is square matrices, we can define single parameter in the equation.
Yeah,
That's my opinion, yeah.
that is also fine. Okay, that's also fine. Okay, but actually in input size is, this is the way. Okay, now to represent this in memory, how much is required? Okay, now how much is required? That is no. Now sum of elements in an array. Sum of elements in array.
Single parameter n.
Single parameter, that is sufficient. Graph, any graph traversal problem.
Yeah, so vertices and edges.
Yes, and the vertices, number of edges and number of vertices.
Both. Okay, no, number of vertices and number of edges. And number of edges. Is that okay?
Fine, sir.
Okay, we'll come to this input size after some time. Okay, no? Okay. Next one. So what does this algorithm mean? How it actually originated, the word algorithm originated, that we'll see now. Okay. So if you consider first 5 letters of this word algorithm, algor. Algor means in Latin to be cold. And in first, okay, no, 4 letters algo and yes, if you add algos, it means pain in Greek language. It is in Greek language, it is in Latin language. So from this, it is clear that neither algos nor algor is root word of the word algorithm. Neither algos nor algor is root word of the word algorithm. Root word of the word algorithm. Okay. Then how did the word algorithm actually originate? Actually, the word algorithm originated from the name of Arab scholar Al-Khwarizmi. His full name is Abu Ja'far Muhammad ibn Musa Al-Khwarizmi. Al-Khwarizmi. Okay, so whatever number system we are using now, what is the system, most popular system in the world? Number system?
Decimal number system.
Decimal.
What are the digits in that? That is 1, 0 to 9. This is decimal system, no? Decimal system. Earlier, what was the system that was more popular? What was the system that was more popular
Roman.
before
Roman
11th century and all?
Binary number
Roman. In Roman, if you want to represent number, this is 1, 5, this we know, no, X, 10, L, M, D, something like this. Okay. So doing calculations, is it easy in Roman system or in decimal system? In order for
Decimal system, it is much easier.
performing multiplication, is it easy in Roman system or our decimal system?
Decimal.
Decimal is very easy, no? In Roman, no. First of all, to represent a number itself, we struggle. Okay, no, 56, if you want to represent, that itself is a big task. Okay, forget about doing calculations. So till then, okay, no, that was more a popular system. Later, okay, no, in 9th century, this Al-Khwarizmi, he spread the use of this decimal system, which we are calling it as 0, 1 to 9 digits, no, in that system, that decimal system, which was, fortunately, it was originated in India itself. That's why it is also known as Hindu-Arabic system or Indo-Persian system. Okay, no, Hindu-Arabic system, Indo-Persian system. And Al-Khwarizmi in one of his book, okay, no, that is on the calculation with the Hindu numerals, okay, no, Hindu numerals. In his book, he clearly mentions how to do calculations with this Hindu numerals, means this decimal system, 0, 1 to 9 digits, 0, 1 to 9 digits. And he also clearly explained how to systematically solve linear as well as quadratic equations. Linear as well as quadratic equations. Step-by-step procedure to solve linear as well as quadratic equations. So Al-Khwarizmi clearly explained what is step 1 we need to do, step 2, step 3, step 4, so that we get what are the roots of given quadratic equation. So that means step-by-step procedure he has given to solve this quadratic as well as linear equation. And that book, it has become popular and it was translated to Latin. In Latin, what they have done is, even his name, Abu Jafar Muhammad ibn Musa al-Kharizmi, no, that al-Kharizmi's name they translated, and it was difficult for them to pronounce. That's why they translated it as algorithm. So now please tell me, how did the word algorithm originate? How did the word algorithm originate? How did the word algorithm originate? The word algorithm originated from the name of Al-Kharizmi, who is also considered as, okay, no, most of people consider him as father of algebra, Al-Kharizmi. Why? Because he was the person who initially studied how to solve this linear as well as quadratic equations systematically. That means in procedure way of doing. First step, second step, third step, fourth step. You follow the steps, you arrive at solution to the equation, roots of that equation. Okay. From his name, this word algorithm actually originated from. And this is his, okay, now Al-Kharizmi. And what is next? What is an algorithm? What is an algorithm? So there is no unique definition for algorithm. Different textbooks, they give different definitions of algorithm. But what is an algorithm? It is step-by-step procedure for solving well-defined or well-posed problems. It is a step-by-step procedure for solving well-defined or well-posed problems. Or say there are other definitions, a sequence of computational steps that transform input to output. Also, these are different alternate definitions for algorithm. Okay, different alternate definitions for algorithm. Okay. So simply, if I write some sequence of steps, can we? Okay, we are given a computational problem. Computational problem is given to us. Computational problem is given to us. If I write sequence of steps, 1, 2, 3, like that, is it? Can you call it as an algorithm? This is step 1, step 2, step 3, and this one says step last. Can you call it as an algorithm? We are given a computational problem. We have written sequence of steps, okay, to solve that problem. Simply, if I write some sequence of steps, can you call it as an algorithm to solve that problem? No. According to Donald Knuth, okay, so this algorithm, no, it should have some 5 important properties. One is input. So what is input? It is clear. So 0 1 quantity should be supplied as input. And what is output? And next important things are these 2. What does definiteness mean? What does definiteness mean? That means there should not be any ambiguity in the steps which are given here. There should not be any ambiguity in the steps which are given here. That means whoever reads, all should understand it in the same way. There should not be any scope for different interpretations of the steps. There should not be any scope for different interpretations of steps. Okay, that is the meaning of definiteness. Okay, no, unambiguity. Okay. Next, what does finiteness mean? Does it mean that the algorithm should have finite number of steps? Does it mean that the algorithm should have finite number of steps? That means 1 to 10 steps, or only 1 to 20 steps. Step 1 of the algorithm, step 2, step 3, like that to 20 steps. Can you say that it is finite? There are 20 steps like this. Can you say that the finiteness property is automatically satisfied? If there are 20 steps in our algorithm, can you say that the finiteness property is automatically satisfied?
Yes, it is satisfied.
No, that is important step. The number of steps in the algorithm, no, it is not finite. Okay, it is not number of lines in that algorithm we write. It is what does it mean? It is, for example, if I write one infinite loop here, infinite loop in third step, is it finite?
Then it is not finite.
Is it finite?
No, if it is infinite loop, that means the process is not going to be complete. So it is not finite.
But that means it is not terminating after finite amount of time, no. Okay, so it does not mean that number of lines in that algorithm is finite. It means the algorithm should terminate in finite amount of time. Okay, no, it means the algorithm should terminate in finite amount of time. So what does it mean? What does it mean? What is time here? Our algorithm should terminate in finite amount of time, we are saying, no. So what does time mean here? What does time mean here? Okay, that will come back to that. Okay, before that, what does effectiveness mean? What does effectiveness mean? So in algorithm, no, we should not combine many things into one line and we should write. Okay, no, it's not like that. Okay, it should be simple and it should be we should be able to perform the task. Okay, no? So for that purpose, we write functions and all that is different. Okay. So importantly, we need to understand what does finiteness mean, what does definiteness. Definiteness, it is clear in unambiguity. What does finiteness mean? That we elaborate on that. Okay. So we have understood that it is not number of lines is finite. This is not correct. This is not correct. Number of lines, no, in the given algorithm is finite. Then what is finiteness? What is finiteness? So if an algorithm is given, this is algorithm. So here we actually give some name of the algorithm name. And if there are some parameters. So this is say step 1, step 2, step 3, and so on, say last step. Step last. Is that okay? Okay. Now each step of algorithm, what is that we perform here? Whatever line we write here, what is that we perform? What is that we perform here? Any algorithm you take, each step of the algorithm, what is that we perform?
Some computations we perform in
Some
that.
computation means either some arithmetic or logical operation, no? Each step of algorithm, we perform some operations. Mostly they are in arithmetic or logical operations. Is that okay? Why? Because this CPU, whatever CPU we consider, it has arithmetic logical unit. So it performs mainly some arithmetic or logical operations. So any algorithm you write, inside any step of that algorithm, you see some arithmetic or some logical operation will be there. Some arithmetic or some logical operation will be there. Okay, some option. Then each step of, so we write it to solve some computational problem. Okay, no? To solve computational problem, we have written an algorithm. So definitely there will be some input size here. Okay, no? This problem, some input size will be there. Input size. Now each step, what is the operation that is performed? Operation performed. We can write each step. For example, here something like this is there. So C equal to A plus B. That means what is the operation that is performed in third step? What is the operation that is performed? We can write it as addition. So like that, each step you write what is the operation that is performed. Like that last step. Next, each operation, what is the number of times it is performed? Number of times it is performed. Number of times it is performed. Say in the first step, I call it as, in the first step, it is performed, say T1 of n times. Why n? I can say it as input size, T1 of n. Operation performed is some operation, say this is say comparison operation or something. Okay, no? Some automatic. Okay. Whatever operation is performed, that is performed, say T1 of n times. In second step, operation performed is something, okay, or say subtraction or addition, that is performed T2 of n times. In third step addition, it is performed say T3 of n times. On this one last step, whatever operation is performed, say that is performed T last of n times. Is that okay? Is that okay? Now you tell me, in this entire algorithm, what is the total number of operations performed? What is total number of operations performed in this algorithm? Total number of operations performed. Total number of operations performed.
It depends on number of instructions written here, steps written here.
That we can, okay, because this I have made it parameter. So we can say that number of operations performed in step 1 plus number of operations performed in step 2 and this one number of operations performed in last step. No, so we can write this as, we can write it as sigma I equals to 1 to last. 1 means step line 1 or step 1. Last means last step. Ti of n. Is that okay? Is that okay? This last, it may be 5 or 6, or it may be, if you write 1 lakh lines, then this last value will be 1 lakh. Okay, that doesn't matter. So then what is the total number of operations performed? Sigma number of operations performed in step 1 plus number of operations. So what is this value? This is T1 of n plus T2 of n plus T3 of n plus on this one plus T lost of n. Okay, this T lost of n, that is total number of operations performed. This in simple terms, I can write it as T of n, where n is input size. So T of n is this value, total number of operations performed in our algorithm. Total number of operations performed in our algorithm when n is input size, where n is input size, where n is input size, where n is input size. This is the total number of operations performed in our algorithm. Is that clear? So in any algorithm, we have different steps. Each step, some operation will be performed inside it. So you write down what is the operation that is performed and how many times that operation is performed. Like that for each and every line or each and every step you write, then take summation over all steps. Then we will get overall what is the total number of operations performed in our algorithm when n is input size. Say I have taken one parameter, so n is input size. N is input size. Okay. So this is total number of operations performed. Now what we are saying is an algorithm is said to be finite. An algorithm is said to have finiteness property if this T of n is finite. What is this T of n actually? What is this T of n actually? What is this T of n? It is only operation count, no? Operation count. That means number of operations performed in our algorithm when n is input size. Is that correct? What is T of n here? Total number of operations performed in our algorithm when n is input size. Is that correct? Is that clear? So when do you say that our algorithm has finiteness property? When do you say that our algorithm has finiteness property? When do we say that our algorithm has finiteness property?
T of n is not infinite.
T of n is finite. T of n is finite, where n is input size, where n is input size. So this, how to calculate T of n, that we will be seeing with different examples. Okay, now that we will be seeing with different examples. So that is finite. That is the meaning of finiteness property. That is most important thing. Next, what is next question? What is next question? What is our goal? To solve a computational problem, we write an algorithm. We write an algorithm which we want some computing device to solve it for us. Okay, we have written an algorithm. Okay, now and we know that that algorithm has to have these 5 properties: input, output, definiteness, finiteness, and effectiveness. All this fine. Next, what next? When do you say that simply if I write like this, can you call it as an algorithm? Or when do you say that this algorithm is actually correct for the given problem? When do you say that our algorithm is correct for given problem? So any algorithm, we clearly say no, for what type of input it works. For what type of input it works, what is the output which is expected from that? for what type of inputs it work, and what is the output it is expected from that, no? What is the output that is expected from that? So for whatever inputs we mention here, for each and every input, each and every possible instance of that input, it should give correct output. Then we say that our algorithm is correct for the given problem. For each and every possible instance, all instances, it should give, okay, given in the possible instances, all possible instances, it should give correct answer. Then we say that our algorithm is correct. Then we say that finally our algorithm is, ALG means algorithm is correct. So this is about correctness of algorithm. Even for one instance, if our algorithm doesn't give, can we say that it works for all the inputs which are given in the input? All the instances which are given in the input, is it correct algorithm for that problem? No. Why? Because there are some instances for which it fails, no? For which we need to, then we need to change input or some restrictions. Okay, we need to fix. Next question is, okay, we have an algorithm, this something like this, okay. Next question is, because we are going to run this on some computing device, no? On some computing device. That means it should be simply, if I write algorithm in sheet of paper, what is the use? No, it's not used. So that means this algorithm should be converted to what?
Program or
It's
software.
a program. That program should be given in the language in which that our computing device understands, no? In the language in which computing device understands. After that, what is our goal? What is our goal? So now we need to find out, okay, this is my computing device. This is my computing device. I have written an algorithm. This is our computing device. Okay, a computing device. Then on this computing device, what is the amount of time our algorithm takes? That's what we need to calculate or estimate. We need to calculate or find or estimate. So given on what this algorithm, next step is on what type of machines or computing devices you are going to run that corresponding program. Okay.
So your voice is not audible.
That we need to fix now. So our goal is this algorithm, what is the amount, if I convert it to program, that program, if I give input, then we get output. To transform input to output, what is the amount of time that algorithm takes? Okay, that algorithm takes. In order to find that, what is that we need to do? We need to first know on what type of missions we are going to run this program which is based on this algorithm. On what type of missions we are going to run the program which is based on this algorithm. Why? Because if the type of computing device is different, the amount of time also varies. No, the amount of time it takes also varies. Why? Because for example, if we have a scooter, we have say scooty. So if you ride that scooty in normal roads, it might give say 45 or 50 kilometers per liter mileage. 50 kilometers per liter mileage. Okay, 1 liter petrol, we can go on 50 kilometers. Same bike, say if you ride that in highway, you might get say 55 or 58 kilometers where there are no speed breakers and vehicles are not coming in opposite direction. Then it might be 58 kilometers. Okay, the same scooty or okay, no, if you ride in Thar Desert, that air full of sand is there, what is the mileage that we get? It might be only 5 kilometers or 10 kilometers, something like that. That means same bike, same person is riding the bike. Still, if the road conditions are different, the amount of time it is taking changes, no? It is changing, no? The amount of time it is taking, no? That it changes. So similarly, here also, depending on the computational device that we use, depending on that, the amount of time our algorithm takes, that also it changes. Next question that we need to fix is, what is the computational device, or what type of computational devices we are going to run the corresponding program? Okay, no, the corresponding program, that we call it as computational model. That we call it as computational model. That we call it as computational model. So if the computational model is different, the time whatever it takes, no, that and all becomes different. They become different. Okay, they become different. So the computational model which we are considering here for finding the number or total time our algorithm takes is random access machine model of computation, RAM model of computation. So this is the computational model. So what are the assumptions under this model? Okay, now what are the assumptions under this model? So each operation, each instruction, that means here it is inside that is operation. Each operation takes constant time. Each operation takes constant time. That means whether it is addition operation or multiplication operation, both take same time. Both take same amount of time. Similarly, whether it is a subtraction or division, it is going to take same amount of time. There is no difference. There is no difference. All operations take same amount of time. And one more important thing is here there is no parallel execution. Parallel execution. That means what? If after completing first step, then only you go to step 2, next to step 3. There is sequence one after the other in the order. Okay. Next, loops. If it is something we write, no, like for I equal to 1, I less than or equal to n, I plus, something like this. They are not considered as single operations. They are not considered as, for example, a of I equals to a of I plus something 2, something like this. If you write, no, so they are not considered as one operation. They are considered as different operation, more than one operation. Okay. Loops and they are not considered as simple operations. Simple operations, again, it is constant time. Okay. Next, most importantly, it has infinite amount of memory. Theoretically, it has infinite amount of memory. This is memory. And one more important thing is whether data is here, or it is here. That means irrespective of its position in the memory, same amount of time we can access. Same amount of time to access that. But actually, if we want to access, no, for example, a Turing mission, if you consider from this side to this side, if you go, okay, no, here to access this and to access this, whether the same amount of time it takes? No. Why? Because you need to scan, no, from left to right, so the amount of time will be different. But here under this model of computation, under RAM model of computation, irrespective of its physical location in the memory, each data item accessing that memory access, it takes same amount of time. It takes same amount of time. Is that okay? So what are important assumptions under this computational RAM model of computation? All operations take same amount of time. One more thing is, what is next thing? There is no parallel execution. Next, loops and subroutines, they are not considered as simple operations. Okay. Next, each memory access, this is called random access. This is called random access to memory. No, this is the meaning of random access. No, actually, this is random access. So the model that we are going to consider is to calculate what is the amount of time our algorithm takes. Okay, what is the amount of time our algorithm takes? No, so the model we are considering is RAM model of computation. That means that in that scooter case, no, we are fixing on what type of roads we are going, highway or something, normal roads or something. Okay, like that. Here it is RAM model of computation. Next, what is under this RAM model of computation? What is running time of an algorithm? Under RAM model of computation, what is running time of an algorithm?
Number of steps taken by the problem.
What is number of steps mean here? That we have already calculated. Now, what does number of steps mean? What does number of steps mean? Number of steps mean here whatever we calculated. No, it is number of operations. Number of operations. This is operation count. This loosely speaking, we call it as hereafter running time. Is it exact time? Is it exact time? Running time means is it exact time?
No.
Is it a time value?
Estimate time.
Or number count?
It's an
Is it in
empirical.
hours or seconds? Is it something like that?
Analytical.
No, it's not that value. It is number of operations performed in our algorithm. Number of operations performed in our algorithm. But you might get some doubt. So this is okay. This is following RAM model of computation. RAM model. But if I want to exactly calculate what is the amount of time our algorithm takes, what is the amount of time our algorithm takes? Okay, that means the corresponding program takes. How to calculate that? So they actually know for any specific device, they give manual, what it says, what operations, what is the time it takes, what is the time it takes. So if we add time for each operation, say first operation it takes C1 amount of time, second operation C2 amount of time, third operation C3 amount of time, last operation C last amount of time. Then what is exact time roughly if you want to calculate? It can be Ci into Ti of n. Sigma I equal to 1 to last Ci into Ti of n. Ci into Ti of n. But this C values, no, it varies from mission to mission. It varies from, although they are RAM model of computation, it varies from one computer to another. That's why we don't even consider this. Anyhow, these values are constant. No, these values are constant. These values are constant. Okay. These values are constant. So this we call it as running time. What is running time? Running time is, you should understand it as only operation count. Number of operations performed in our algorithm when n is input size. When n is input size. When n is input size. So now here simply you tell me how many operations are performed in this algorithm. Here in, okay, what is this algorithm? It doesn't matter to us. What is input size here? We are given an array. We can easily find out. No, here throughout this course, I consider array indices from 1 to n. Instead of 0 to n minus 1, I consider array indices from 1 to n. 1 to n. So now here what is the operation that is performed? Say assignment operation. Assignment operation performed. Operation performed. Operation count. How many times it is performed? One time. What is the operation that is performed here? Here we are actually combining many things in second step. So we can consider it as comparison operation, increment, many things are happening here. Okay, let us call it as some operation, say comparison operation. Comparison operation. How many times that comparison operation is performed here?
N
N
times.
plus 1 time.
Some people they consider it as n, some they lost to comparison where it fails. No.
N plus 1.
N plus 1. It doesn't matter whether you take it as n or n plus 1.
Yes.
Okay, it doesn't matter. Okay, it is immaterial. Okay.
Mm.
Okay. Now, how many times this operation is performed? What is the operation that is performed here? Addition. How many times it is performed?
One time.
N.
Okay.
One time, like that it is performed for each value of I equal to 1 to n one time. This value is, what is this value? What is this value? Okay, this anyhow we will discuss in detail later. N times it is performed. So this is written whatever operation, this written operation, this only one time it is performed. Now you tell me what is total number of operations performed here? T of n, 1 plus either n or n plus 1, whichever we want, we can take, plus n plus 1, which is
2n plus 2.
2.
Oh, yeah,
This is
it is
actually,
n,
this is called, this is called
total running time.
running time.
Running
Actually,
time.
is it running time? Is it running time? No, it is actually
Order of
operation
n time.
count. Operation count.
Okay, okay.
Operation count means number of operations performed in our algorithm. Okay. So this is the way that we calculate, that we will discuss when we actually go for how to do this. Okay. This is running time of this. Similarly, some other algorithm is given like this. Here also we can count now how many times each step is performed. Then total T of n value we can calculate easily. Okay, like that for different algorithms. In general, if we are given different step, each step we can calculate, then we'll get T of n. So finally we can calculate T of n. This, if I can say that T1 of n, this is T2 of n, this is T3 of n, and this is T6 of n, number of times count. Then finally Tn is that summation only. Sigma equal to 1 to n, Ti of n, 1 to 6, Ti of n. Is that okay? That is, this is our running time or operation count. Running time or operation count. Same thing, we call it as operation count. Next question. Okay, this is, what is the amount of time our algorithm takes when I go for implementation? How do we calculate that? How do we calculate? Okay, this algorithm is fine. This algorithm, some find algorithm, something. This is outline only. Okay, this algorithm, from this I will get a program. I'll get a program. This, if I give input, it gives output. To transform input to output, what is the amount of time it takes? Amount of time it takes. How to calculate this?
We need to do empirical analysis where at the beginning of process, we measure the time. At the end of process, again, we measure the time. We find the difference.
Okay.
And we do it for all the possible inputs.
Okay. So, but practically, so what sir is saying is, we need to implement in this case. We need to implement. Then after implementing all instances, majority of the instances we give instance one, what is the time? Instance 2, what is the time? Like this, last instance, what is the time? Like this, if we want, we can calculate. Okay, we can calculate. But say, now if I ask a question, to solve a problem, we have two different algorithms. Both are correct algorithms, algorithm A and algorithm B. Both are correct algorithms. Both solve the same problem. Okay. Now, any algorithm, what are the resources any algorithm requires? When I go for this implementation, what are the resources the algorithm requires? What are the resources that algorithm requires? The moment I go for program, this program I need to store in memory, so some memory is required.
And space. Space and time.
This input should be transformed to output. Some time is required. What is time here? We can consider this is CPU time. No, these are the two resources mainly we talk about. Okay, now these are the resources that our algorithm requires. Okay, now we can compare. Say I have a problem. To solve that problem, I have two correct algorithms, A and B. Which algorithm is better? Which is better is the question now. So input size, I am considering it as n. Input size is say n. Which is better? Which is better? Which is better? Are you following? Is the question clear?
Less time and optimized results.
Memory.
So out of this, madam is saying whichever algorithm takes less time.
and optimized results.
Out of these two, whichever algorithm takes less time, that algorithm is better. Now the question is, time means, are we talking about this time after going for implementation and for each instance checking the time? Then we are we going to decide which is taking more time? This is execution time, we can call it as. Okay, now to differentiate from that running time, no, this is execution. Okay.
Actually, we need to find out the behavior
Yes,
of
sir.
runtime. And based on the behavior of runtime, we can decide which algorithm is better.
So, okay. So that means now you are saying, sir, that we need not to go for implementation itself. That is your point,
Yeah.
sir. Is that
Yeah,
correct?
yes. We should not go for implementation.
Then next question is, why shouldn't we go for implementation without even going for implementation? Why do we decide? So okay, now for those we have not understood, see, algorithm A is there. Okay, now algorithm B, both are correct algorithms. Which is better means whichever takes less time, we are saying that algorithm is better. Whichever takes less time, that algorithm is better. But how to calculate time? So from the algorithm, we get a program. That program specific instance we give. That instance, from that we'll get output, input to output. And what is the time it takes, we calculate. Each instance, what is the time it takes, calculate. Similarly, here also instance 1, algorithm B also instance 1, instance 2, instance 3, some last instance, we calculate the time. We calculate time. Then how do you decide which is better? How do we decide which is better? See, algorithm A, we can give different instances and calculate time. Algorithm B also, we can give different instances and calculate time. Then finally, how do we decide which takes, which is better, which is more efficient? Which is more efficient?
See, in this way, it depends upon the device also. Also, during the runtime, there are many other factors. What are the other applications running? What are the background services? So this way of computing time will not give accurate result.
Okay, what is one problem with this way of calculating it? Thank you, sir. One problem with this way of calculating is, okay, let me take a new sheet. So, so we have to solve a problem. We have two different algorithms, say algorithm A and algorithm B. Input size is n. Input size is n. So which is more efficient is our question. Both are correct algorithm. So for example, this algorithm A is good. Okay, algorithm B is not that much good. But the student, the one who has implemented algorithm A, used better proper data structures inside, because depending on the type of operations we perform, we need to cleverly choose data structures. Okay, no, data structures. Algorithm B is not that much good. Okay, no, okay, not using proper data structures. Here, the one we have implemented used proper data structures, proper suitable data structures, suitable data structures. So then what happens? Same instance if I give, instance 1 to A, it may take more, it is say 100 microseconds. Okay, algorithm, same instance, program, the corresponding program. Okay, no, this I call it as P1, this corresponding program you call it as P2. Okay, it is taking say 82 microseconds. Can we conclude that based on this algorithm B is more efficient than algorithm A? can we conclude based on this algorithm B is more efficient than algorithm A?
No.
No. So why? What are the reasons? Though algorithm is very good here, because the one who has implemented, no, they have not properly chosen data structures. That's why it is taking more time. And the other one is
Program is not good, but taking the good data structures.
Because any algorithm, no, that the heart of that no algorithm is data structure only. No, we don't, even if the logic is very good, if we don't use proper data structures for implementation, automatically it takes more time. No.
Yes.
Automatically it takes more time. Okay. So then, how to overcome this drawback? How to overcome this drawback? And this is one reason. Other reason could be the programming language used in implementing A is different, and the programming language used in B programming language is different. Then also there might be some differences. Our operating system used may be different. Here also operating system, still there may be some differences. Okay, no. It also depends on the capability of the person who actually implements it. That is also a problem. So to overcome all this, what is that we do is, without actually going for implementation, by seeing that algorithm itself, we decide which algorithm is better. We decide which algorithm is better. That means, what is that which we have avoided here? Due to this, no implementation. No implementation. Without actually going for implementation, we decide which algorithm is better. A is better. Okay, A is better or B is better. Say algorithm A, how to do that? You calculate running time of algorithm A, T of n value. What is running time? It means it is operation count. Operation count. Operation count. We calculate in case of algorithm A. So it is say 2n square plus 3n plus 4. Let us say this. In case of algorithm B, operation count is 2 power n plus n plus 1. 2 power n plus n plus 1. Okay, 2 power n plus n plus 1. Okay. Now which algorithm is better? Which algorithm is better? So algorithm
A is better.
Or operation count. This is running time or operation count. Running time is 2n square plus 3n plus 4. In case of algorithm B, it is 2 power n plus n plus 1. Now tell me which algorithm is better?
Algorithm A is better.
Algorithm A is better. But if I take n equals to 1, how many operations are performed in algorithm A?
But while deciding which algorithm is better, we should not look at the only one instance size. We should go with the larger instance size.
Exponential is better.
Okay, this is 4. Yeah, okay. N equal to 2 if we take
2n
square
square
plus 3 into 2 plus 4. Here it is 2 square plus
8
2
plus
1.
4 plus 2, 8, 7.
Sir, while before we conclude, we should always consider the larger instance value of like n1, 2 doesn't matter. If you go for 1,000, 2,000, it happens that after a crossover point, for all the instance value, the algorithm A would be better.
Okay, thank you, sir. That's what I am going to say. Okay, because there are some students who are, BTech studying students also. So n equal to 10 if we take, what is this value? 234. Here it is
2 power 10,000.
1035.
1035.
So now, but for small values, this algorithm, number of operations performed is very less. But for when we go for large values, number of operations performed in first algorithm is very much less when compared with number of operations performed in
exponential
second algorithm. Okay, no, second algorithm. So that means really, if we want to know which is more efficient, that means which takes less time. That means less time is more efficient. We need to, for example, car is there, tractor is there. Which goes faster?
Car.
Most of us, almost all of us will say car only, no? So
Depends
how
on
are we
where you
able to
drive.
say? How are we able to say? If it is distance is 5 kilometers, or say only 1 kilometer. Distance is 1 kilometer.
If you look at only the distance and don't look at the where we drive. If we drive in maybe farm, car will not go faster.
That
Yes.
because okay. So that is because underlying conditions are same. Underlying conditions it is fixed, but okay, it is fixed because both can go properly. Okay, no, it is no such thing is there. It is fair. Okay, no, it is fair competition. It is fair competition. It is a normal road. Here, some person is standing. Say, okay, the Subbareddy is standing here, and okay, says our principal or director is there in his car, and the distance is say 10 meters, and let us say 50 meters, and from here to here we need to reach. Who can reach faster? This is a Subbareddy. This is our say director sir. Who can reach faster? Only distance is 50 meters. Distance is 50 meters. Before his driver, okay, no, starts car and okay, no, before that, after 1, 2, 3, Subbareddy can immediately run here and he reaches here. Does it mean that Subbareddy can run faster than director? It can go faster than director's car? If you really want to know what is the capability of Subbareddy, distance you take 100 kilometers. 100 kilometers. Okay, normal road only. Okay, there is no such thing. Normal road only, distance. Then we will actually know whether this car can go faster or this person can go faster. Similarly, that's why we can easily say that car goes faster than this person. No. So similarly, what we can do here is we take input size very large. As n tends to infinite. As n tends to infinite. What happens? As n tends to infinite. 2n square plus 3n plus 4. Can you say that it is approximately equivalent to 2n square plus 3n? N is very large means whether 4 is there or not there, it doesn't matter, no? That 4 is there or not there, it doesn't matter. If n is very large, this entire thing we can write it as approximately equal to 2n square also. It is lakhs of crores. Then 2n square crores square, it will dominate this term. So in that case, if n is very large, this also we can approximately write it as equal to n square. We can approximately write it as equal to n square. So what is that we have done here? In given T of n means running time, we have dropped all lower order terms. All lower order terms. These are lower order terms, no? Not only that, constant coefficient of highest order term. In this T of n, what is constant coefficient? Highest order term is this. In this, what is constant coefficient? Only 2. So that means in running time or operation count, we have dropped all lower order terms as well as constant coefficients of highest order term. Then whatever remains, that we call it as order of growth or rate of growth. Order of growth or rate of growth. Or rate of growth. So how to get order of growth or rate of growth? How to get order of growth or rate of growth? After get of algorithms running time, first calculate running time. In running time, drop lower order terms. Lower order terms. For example, if Tn is 2n cube plus 6n square minus 70n plus 20. So what is order of growth here? What is order of growth? What is order of growth here? What is highest? What are lower order terms? What are lower order terms?
N square, N 20.
These 3 are lower order terms, no?
Yes.
So only n cube.
Only n cube.
3 we neglect. Not only that, what is constant coefficient here? This is 2. This also
2.
we remove. Whatever
Yes.
remains, that is for large values, it is same as n cube. approximately equal to n cube. This we call it as order of growth or rate of growth of T of n. T of n. Is that okay? What is order of growth or rate of growth? Is it clear? Is it clear? What is
Yes,
order of
yes.
growth or rate of growth in case of B? What is order of growth? Here after OOG I use for order of growth. What is order of growth in case of algorithm B?
Algorithm B, exponential 2 power n.
2 power n. Thank you very much.
Order of n, order of exponential, it is 2 power n.
This is 2 power n, madam. This
Yes.
is 2 power n. Now, here what is order of growth? This is n square. Now, final point is which algorithm is better means whichever algorithms running times order of growth is lower, we say that the corresponding algorithm is better to solve that problem in general. Okay. So now out of A and B, which algorithm has lower order of growth? Algorithm B has lower order, algorithm A has lower order of growth. Hence we say that algorithm A is more efficient than algorithm B, or algorithm B takes more time than algorithm A. Is that okay? So final point is whichever algorithm has lower order of growth,
Lower order of growth.
that is better or more efficient. More efficient. Is it clear? What is order of, because this term we need to understand, okay, no? Order of growth or rate of growth, okay, this most important, this we will be using throughout this course, okay, no? Is that clear? What is order of growth or rate of growth? Now, next, we know what is order of growth, rate of growth. Next, what does complexity of an algorithm mean?
How much time and memory is required?
How much time it, what amount of resources that the algorithm requires. Mainly we talk about CPU, two resources that I have already mentioned, CPU time and memory. Okay. Now here, are we going to calculate the amount of CPU time after implementation? Based on implementation? Out of these two resources, which is more valuable resource? Out of CPU time and memory, which is more valuable resource?
CPU.
If I want to double CPU space, CPU process speed, if I want to double memory, okay, no, then what is the amount of money that we need to spend? That if you can think, then automatically we'll get answer for that, no? Out of these two, it is more precious resource, no? More precious resource. Okay, so that's why most of the time now we talk about this only. We talk about this CPU time, CPU time. So next, given an algorithm, anyhow we are not going for implementation. We are not going for implementation. Without implementation, we need to find, by looking at this algorithm, we need to find order of growth of that algorithm. Order of growth of that algorithm. Is that okay? Order of growth of that algorithm. And without going for implementation, what is that we are actually calculating here? Running time value we are calculating, no? Running time value we are calculating. It indirectly tells me what is the amount of time that the corresponding algorithm or corresponding program takes when we go for implementation. That means before it happens, we are actually predicting that, no. This is called, we are estimating that, no. So this is called analysis of algorithms. What does analysis of algorithm mean? What does analysis of algorithm mean? What does analysis of algorithm mean?
Estimation of the.
That is predicting the resources, simple terms, predicting the resources, predicting, or that means estimating or estimating. Predicting the resources the algorithm requires. resources the algorithm requires. Predicting the resources the algorithm requires, that is known as analysis of algorithm. Analysis of algorithm. That means we need to predict how much CPU time is required. Why are we saying that we are predicting or estimating? We are not actually going for implementation, no? By looking at algorithm itself, we are saying, okay, no? By seeing that algorithm itself, we are saying, okay, this is called analysis of algorithm. What does analysis of algorithm mean? Estimating the amount of time our algorithm takes when we go for implementation, estimating the amount of space our algorithm requires when we go for implementation. That is called predicting the resources. That is called actually analysis of algorithm. That is called analysis. But what type of we are actually predicting here? We are actually predicting here? Are we estimating time and space? Time? Are we estimating time here? T of n value we are estimating, no? After calculating
Yes.
T of n, what is that we are doing? Dropping lower order terms
And constants.
constant coefficients of highest order term.
Hmm.
Constant coefficients of
Highest order terms.
Highest order term. Constant coefficients of highest order term. So after that, whatever we get, that we are calling it as order of growth. Okay, that we are calling it as order of growth. Next. Now we know what is order of growth. That means we know how to analyze algorithm. Okay, how to analyze algorithm. That procedure we don't know. What does order of growth of algorithm running time? That much we know. What is order of growth? What is order of growth? That much we know. Okay, let us take one or two examples. 4n key plus 5n minus 6. What is order of growth here? What is
NQ.
order of growth? It is NQ. So now that means here we are calculating order of growth as n tends to infinite. No, that means what? Are we analyzing it or not? Analyzing. We are analyzing algorithm only. That means we are predicting what is the amount of time required. But how are we analyzing it? With some restriction. Based on n tends to infinite. No, what does it mean? For large values of input. For large values of input. For large values of input size. Okay. This way of analyzing algorithms is called asymptotic analysis of algorithms. This way of analyzing, analyzing amount of time required for large values of input. So this is called actually asymptotic analysis of algorithm. Asymptotic analysis. What does analysis of algorithm mean? What does analysis of algorithm mean?
Predicting the resources.
The resources that the algorithm requires. We most of the time we talk about time only. Next, what does asymptotic analysis mean? Here we are actually doing prediction for large values of input only without actually going for implementation. And this way of analyzing algorithms, that is called asymptotic analysis of algorithm. This way of analyzing algorithm is called asymptotic analysis of algorithms. So I just stop here. Okay.